This is the Vika Academy. Today we want to look at real valued functions of symbol variables. If you have not subscribed to this channel, kindly subscribe and also share with your friends so that every time I post anything here, they are the first one to get the notification. So this is real analysis, and it's actually introduction to real analysis. Real valued functions of symbol variable. So this is a function which domain is an interval and range is set of real numbers. So if you find a function that its domain is an interval and you find that the range is a set of real numbers, then you call that one a real valued function. For example, if we let this f be defined in this, define as that as follows, that if a function of x, if it's a rational number, then we have 1, and if we do it's a rational number, we have -1. If you look clearly at this one, this example here, you'll find that the domain is actually that, and the range is this. So if you look at this one, we are having a domain which is an interval, as you can see, and we are having a range which is a set of real numbers. It's a set of real numbers, and therefore this kind of function is what we are calling real valued function. Okay, let's look at graph of a function. So if a function x maps which maps to y, x to y, then the set ordered xy on which x is in x and y is in y is called graph of f. So this ordered set here is what we call graph of function f, in that the x is in y, is in x, and the y is in y. That's what we call graph of f. So we divide it like this: x fx such that x in y, and this one fx is in y. That's the ordered set, and it's actually what we call the graph of a function. Now every ordered pair x of fx, or ordered pair of that form, corresponds to a point in xy plane, and vice versa, So every set pair here correspond to a given point in xy plane. Okay. Now, for example, we can look at this. If we have a given function, we consider a function of x, which is 1 over sine 1 of x, and this of course is when x is never equal to 0, so that becomes undefined. Then you say that if you take when x is equal to, when fx is equal to 0, you see that we have x being 1 over pi, 1 over 2 pi, 1 over n pi, that way. So that if you were to sketch this, you'll find that you get this kind of a curve here. You get this kind of a curve here, such that the upper limit here of this is actually 1, and here is -1. So it will find that y lies in between that point, and this is actually the demonstration graphically what we are calling graph of the function. And this is the graph of this function, which is sine of 1 over x. So if you take x to be 2 over pi, for example, you find that is 1. If you take x to be 2 over 3 over pi, then you'll find that that is actually -1. So odds gives you this down part, these are odd, and evens give you the upper part here, evens. So that's how you demonstrate that. So you'll find that every value in x is also in that, and the value in fx is in y. So every on and pair in that correspond to a point in x plane. Okay, let's look at another key thing about function. Another property is called boundedness of a function. Boundedness of a function. We say a function f is bounded if there exists a given small m and a capital M such that the capital M is less than the function and the function is less or equal to the capital M. Capital M for all x in the closed interval AB. So the small m and the capital M are called lower and upper bounds of f respectively. So the upper part of the function is bounded by m, capital M, and the lower part of the function is bounded by small m, and ends lower and upper bound of the function respectively. If there exists this ordered set xy in the closed set AB such that fx is equal to m, small m, and fy is equal to capital M, then you say the ordered set m, mn, and small m, capital M are called the greatest value and the least value in the closed set. So you find that fx gives you the small m and fy is the capital M. Then you find that this set gives that greatest and the least value of the function. And therefore we say that the supreme of f is capital M and the infirm of f is small m. That's about boundedness of a function. Let's look at another property of a function which is called, we call it oscillation of a function. If a function f is with a domain which is closed MB, such that f is bounded, that means they have a small m and a capital M as we have looked previously, and m, capital M and small m are bounds as we have just said of f, then you find the absolute value of the capital M minus m, which is the upper bound minus smallest bound, least bound, is called the oscillation function of f in the interval MB, which of course is the domain of the function. It's the domain of the function. Okay. So what you need to know about this, the remarks that you need to know is that if you have a small capital M, that's absolute, being greater or equal to the function of given x1 minus the absolute of x2, of the function value function, so this is the key remarks that you need to note. At any given time, the oscillation will be greater than any function of x is in. Of course, these x1 and x2 are in the domain A, B, so they are inside. Remember, m, capital M and small m, they are either greatest and the lowest, the least. So that means if you take either value of the function in this, they will be lower than the oscillation of the function. Okay. So if a function is not bounded, if the function is not bounded in the domain of f, then the oscillation of the function is infinite. So if you find that this one is not bonded, so that means that does it have the upper bond and the lower limit, then it will mean the oscillation here will be infinite. It will be infinite. It will be infinite. I think that is the key remarks that you need to note on that about oscillation of a function. So if you have not subscribed to this channel, kindly subscribe so far. Also, make a trip across my channel. Look at most of the things that I'm posting. They have good tutorials, and also refer your friends to this channel, and remember to subscribe. Okay, example. Let f be defined on R such that if you have 1, if you have a rational number, and we get -1 when we have a rational number. Now, in this, we can point out the supreme of f. So you'll find that m is the upper bound, which is also the max is 1, and small m is the minimum, which is also the minima, and it's a -1. Therefore, if you want to get oscillation, remember the formula: m minus small m and the absolutes, and therefore you say is 2, and that is it, Now kindly subscribe and remember to share with your friends.